Note that this control algorithm will be replicated for both the pan and tilt servos, so that's running in parallel. But we chose to implement a discrete proportional integral derivative control algorithm that runs on the DSP. So after it finishes doing all the center of mass, and this is passed through a PID controller whose gains can be set in the defined state. And of course, with a control algorithm, a discrete control algorithm, you need to know how fast it's refreshing. So the only thing is the refresh rate is dependent upon how fast the DSP can process frames. So that's approximately 10 hertz. And using the Ziegler-Nichols method to kind of tune it, and then playing with it a little bit afterwards, we're able to get some pretty good results where we have a settling time under 2 seconds, a rise time under 1 second, to the percent overshoot of less than 30%. Now note that these values have not been measured quantitatively. I mean, we haven't hooked up a probe to the servos to read off the actual positions, but we invite you to come outside and take a look at our demo, and I think you'll agree that the motion looks very smooth and very nice. So now I'm going to pass it on to Bill, who's going to talk about our testing procedure.
For testing, we used a bright single-colored object that's hung on the end of a pendant, and we use this test to basically see how capable the camera is to track this object at different speeds. And what we found out is that the maximum angular velocity of the servos of the camera was about 150 degrees per second. And the maximum servo velocity is about 300 degrees per second. And so, about advanced applications, as for, we have this peripheral board that can demonstrate the capability and power of the nanoboards that we have, the ND2 and the NanoBoard 3000. And there are numerous applications. There are the object tracking application, facial tracking application that we'll play around a little bit, that can benefit from the versatility of the FPGA and the raw power of the Blackfin dual-core DSP processor. And here's an active.
Finally, we would just like to acknowledge the people that made this all possible. So, of course, we would like to thank Dan Sender, our customer, and Altium, and also the professors and GTFs of senior design. They're the ones who really facilitated this entire process all year. George Bunder was our assembler. He did a great job. It was very nice to help us guide us through the PCB assembling process, and was incredibly generous when it came to pricing. So that was awesome. And finally, I would like to thank Howard Cohen. He was just an invaluable resource. He helped us get sample parts. He helped us save a ton of money. He gave us guidance on how to build a PCB. And he was just, he went above and beyond the call of duty. Finally, this is a summary of just some of our points, and I believe it's time for questions.
From your presentation, it seems like the peripheral board is doing most of the work. What is the main board doing?
The NanoBoard, actually, all that's doing is that's reading the data from the UART and then sending it out to a couple of custom Verilog modules. They're just turning the pulse width modulated signals that are then fed out to the servos to generate information.
Why don't you mention, what did the customer say was or what did you think was the practical application of the project?
I mean, he talked about surveillance applications, so maybe you have some kind of machine learning algorithm where you just look for motion in a room. One thing we briefly discussed was facial detection. But yeah, there's a whole suite of different potential video and imaging applications you can use with this system. It's one of the higher end DSPs offered by analog devices, so you can really do a lot.
You got a machine behind analog PGA, you put it out, especially composite.
What do you mean?
All these NTSC, all the trauma.
I mean, I guess it's just a very, for the particular camera we had a composite output, and I mean, composite output from the camera, composite input to our board, and I don't really know what it is.
So if you go right now and you go to a store and ask, give me a composite output camera, and they would just say, don't have any.
Well, initially, our customer was looking for us. I realized that that doesn't necessarily qualify as a commercial off-the-shelf camera. But we were looking at, surveillance applications. And what we saw, a lot of these do have a composite output.
SPGA library.
Well, in future applications, sure.
There is also the issue of like proprietary information and stuff, so we couldn't simply build like a USB kind of port because it's I mean, we tried putting USB on this, but there's a lot of information.
So speaking of USB, I have this Logitech webcam. It's able to track my use. I'm sure there are other motion tracking systems out there, but what would you say is the novel improvement of this project?
I mean, again, the focus of this project was never about object tracking. The focus of this project was the development of a peripheral board that could provide a platform for future applications. They wanted a board that would interface with their NanoBoard system that could perform digital signal processing. They didn't have that before, so we gave it. The image processing, yeah, it's not extremely complex, but that's not really the focus of the project. It's really
What do you do when you lose the target? What's your, you have an error state?
once you lose the target, the servos just kind of
Wobbles
they
around.
go over, and then we can hit a reset button, and then it will reinitialize to the start.
Once you lose the target, the derivative gain takes over, and it's essentially ballistic. But so initially there was no derivative gain, so the velocity would just lock on center for derivative gain. I don't have any software in there that's saying if the derivative gain is if it's producing constant motion to stop, which would just be an extra feature that.
As an interface board, you demonstrated that the Altium NanoBoard can talk to your peripheral board in some meaningful way?
Currently, the NanoBoard is doing all the initializations for the decoders on the chip, or on the
So there's that multi-master I2C configuration where the DSP and the FPGA are both masters on that same shared bus. So the way we're initializing our decoder chips is the FPGA sends out the initialization signals.
Is there anything else?